Hello, good morning. It's fine. Today we will discuss actually the very important laws of physics to Ohm's law and current electricity. In different way, we will define current electricity here. And with this, we will discuss also some real life example uh, connecting to current electricity. In our previous lecture, we have studied about the static electricity. Now, today we will discuss about the current electricity. So first of all, what is electric current? The electric current is defined to be the rate of change of flow such as that is used to start a truck engine, moves a large amount of charge in a small time. That means the movement of a truck due to a truck engine that is moves a large amount of charge in a small time. So electric current I can be defined as the rate of change of amount of charge with respect to time. If time t tends to 0, then the limit we get q by t. That means electric current I equals to rate of change of charge with respect to time. And which unit is ampere? You must know. Coulomb per second is called ampere. Now, what is electric current? The basic concept of this, connecting the terminals of a battery across device leads to an electric current in which current flows. Charge begins to flow, electric current units will be Coulomb per second, which is called ampere. And the symbol is, you must know, this is the positive part. There will be a positive part and negative part. And if you connect with the voltmeter, B, and the diagram will be like this. These are the symbols of electric current with two parts. One is positive part, another is negative part. Current flow from positive to negative part. You have to remember this. In battery also, it is an electric source. Current coming from positive part to the negative part. Then the bulb will be light on. Now, direction of current. Current is defined to be the direction of movement of positive charge. Current flows from positive to negative terminal. You have to remember this conventional method for the direction of current. But in conductors, electrons are free and carry the charge. Current. So this from this figure, we must observe that electric current passing from the positive charge to negative, but electrons opposite direction. That means electron flow from negative terminal to positive terminal. But positive charge direction will be what? Positive terminal to negative terminal. In the air, electrons move very slowly. That means 0.1 millimeter per second. That means 1 meter per 3 hours. So individual electron will be passed through like this. Now, what if we have a medium with positive and negative carries ion or gas or liquid? Positive ion moves away from the positive terminal. You must know in electrodes, electrolytic theory, positive ions move away from the positive terminal. Negative ion moves towards the positive terminal, but both currents are in same direction away from positive terminal. Now, example of electron flow. Consider a current of 1 ampere. Find the number of electrons flowing past a point per second. That means rate of amount of charge with respect to time will be 1 coulomb per second. So in 1 second, the number of electrons passing through the point is you must know 1 coulomb divided by 1.6 into 10 to the power minus 19, which is the charge of electron. So how many electrons will be 6.2 into 10 to the power 18 electrons in 1 second? This amount electron pass through the air. Now current and electrons drift speed or drift velocity. So the example of this is the example of amount of electrons. Now electric current. What is the definition of electric current? The electric current is defined as the charge flowing through any section of the conductor in 1 second. That means I equals to Q by T per second passing through the charge. If the rate of charge or flow of charge is steady, then I equals to Q by T. If the rate of flow of charge varies with time, then we have to use I equals to dQ by dt. So different types of current here: steady current, which does not vary with time, that means constant, and B and C from the figure, varying current whose magnitudes varies with time. Alternating current whose magnitudes varies continuously and direction changes periodically. So there are two types: direct current and another is alternating current. From the figure, we observe that with respect to time, the movement of electric current, that means which varies with time, is called alternating current, and steady current, which does not vary with time, is called steady. So these are the types of electric current. Now conventional current. Conventional current is the current whose direction is along the direction of the motion of positive charge under the action of electric field. Actually, in the electric field, you must know from previous lecture, current flow from positive charge to negative charge. That means the movement of I will be from positive terminal to negative terminal. Conventional current, due to the motion of electrons, is the direction of opposite to that of a motion of electron. So the current, the amount of charge that flows by an area in a unit of time. So connecting to the electric current flows from the positive terminal to the negative terminal of a battery. Electrons flow from negative terminal to positive. You have to remember this, and which is measured in amperes or in an ammeter. And this is the symbol of current, which is connected with the ammeter. This is a machine which measures amount of electric current. Remember it. Ammeter is a device which can calculate the current amount of electric current. Now we have to use another three terms: voltage, current, and resistance. These three connected with each other. Current is the flow of electron charge through an electronic circuit. The direction of a current is opposite to the direction of electron flow. We already have known. Current is measured in ampere, and historical notes. Henri Ampere, lifetime is 1775, 1836, French physicist. He's a famous physicist of France. So according to his name, we have to denote the unit of electric current, that is ampere. Now another is voltage. Voltage is the electrical force that causes current to flow in a circuit. It is measured in volt. So Alessandro Volta, lifetime 1745, 1827. He was a famous Italian physicist. According to his name, we have to name the unit of voltage. Now another one very important in this lecture: resistance. Resistance is the measure of opposite to current flow. It is measured in ohms. George Simon Ohms, lifetime 1789 to 1854, German physicist, is a famous physicist, and we are discussing actually his law, Ohm's law, here. After a little bit later, we will discuss it. Now, first analogy. This is a very important part. The flow of water from the tank to another is a good analogy for the electrical circuit and the mathematical relationship between voltage, resistance, and current. So force, the difference in the water level, there will be act a force which is called voltage. Flow of water between the tanks, actually it can be say the current. Opposition, the bulb that limits the amount of water. That means the bulb will not let the flow of water, which is called actually resistance. This is the real life example to understand what is voltage, current, and resistance here. Another one, the flash schematic. There are two types of circuit. One is closed circuit, other is open circuit. You must know electric current flowing from positive terminal to negative terminal here, and due to resistance, the lamp is on here. But on the right one, open circuit, no current flow, lamp is off because lamp is resistance, but is not using any energy. But in right but in the on the other hand, left one, the current lamp is on, so lamp is resistance, uses the energy to produce light here. This is the real life example to understand the what is resistance and how it works. Engineering versus science, we have to, as an engineering students, you must know, you have to use the direction of electric current. The direction that current flows does not affect what the current is doing. Thus, it doesn't make any difference which convention is used as long as you are consistent. But both conventional current and electron flow are used. In general, the science discipline use electron flow, whereas the engineering discipline use conventional current. That means the flow of electric current is from positive terminal to negative terminal. Actually, you are an engineering student, so you have to use this concept. Then means electric current flowing from positive terminal to negative terminal. But science discipline use the direction of flow of electrons, which is from negative terminal to positive terminal. Now we'll discuss some important module here. We have to first of all define electric current and electromotive force, right? And only Ohm's law, which is very important law here, to circuit containing the resistance and EMF. Define resistivity of a material and apply formulas for its calculation. Then, so first of all, what is electric current? The electric current I is the rate of the flow of charge Q through a cross section A in a unit of time T. This is a very nice definition. And right one is the figure big where and plus Q amount of charge passing through this cross section area A with respect to time T. So the rate of flow of charge through a cross section area can be denoted by I equals to Q by T. Rate of, and its unit is ampere. So 1 ampere A is charge flowing at the rate of 1 coulomb per second. You have to remember this. The electric unit of electric current, which is called ampere. An example, as an example, the electric current in air is 6 ampere. How many electrons flow past a given point on a time 3 seconds? You must know I equals to Q by T. So I equals to 6 ampere here. So within 3 seconds, what will be the amount of electrons? And now Q equals to 18 coulomb, but you must know the charge of electron is 1.6 into 10 to the minus 19. So we can convert it. How many electrons will be? 1.125 into 10 to the 20 electrons. So within 3 seconds, in 3 seconds, number of electrons moves from one part to another is 1.120 into 10 to the 20 electrons. So imagine a charge capacitor with Q equals to CB that is allowed to discharge. So electron flow, the direction will be what? From positive. Electron flow will be from the negative terminal to positive terminal. But the conventional method, the motion of charge from positive terminal to negative terminal is the same effect. So the electric field and now what will be the electromotive force? A source of electromotive force, EMF, is a device that uses chemical, mechanical, or other energy to provide the potential difference necessary for the electric current. So it is one kind of force. Due to this force, electric current flow on a wire. So there are three types of line: power lines, battery, and wind generator. So due to electromotive force, all device work. So what are analogy of to EMF? Suppose there is a pump connected with the construction. There will be one left will be high pressure and right one will be low pressure. Water coming from the pump, water coming from the pump. So the high pressure due to water, there will be high pressure, and there is a bulb on the right one, so there will be low pressure. So we can convert it into the circuit diagram. So high pressure means high potential, low pressure means low potential, and there is a switch, that means bulb. So source of EMF, that means pump. So resistance will be construction, and water flow will be the electric current. The source of EMF, pump, provides the voltage, that means pressure, to force electron, that means water, through electric resistance, that means narrow construction. This is a real life example to understand the what is the EMF here. Now, the electric circuit, what are the symbols that often contain one or more resistance grouped together and attached to energy source such as battery. That means the following symbols are often used here to understand the electric circuit symbol. One is ground, battery, and resistor. So electric resistance, suppose we apply a constant potential difference of 4 volt to the end of the geometrically similar rod of, say, steel, copper, glass. So steel will be 4 volt, suppose copper will be electric current 4 volt, and glass also 4 volt. The current in glass is much less than for steel or iron, suggesting a property materials called electrical resistance R. That means glass has more resistance than copper and steel. Now, what a very important law, what is Ohm's law? Ohm's law states that the current I through a given conductor is directly proportional to the potential difference B between its endpoints. But you have to remember that temperature and nature of materials will be remain constant. Properties of materials remain constant, and temperature also constant. So Ohm's law, mathematically, I is proportional to potential difference B. So there is a proportionality constant which is depends on the temperature and nature of materials. The Ohm's law allow us to define resistance R and to write the following forms of the law. That means I equals to B by R. So R is the resistance, opposite of electric conductance, and B equals to IR also. R equals to B by I. So Ohm's law can be expressed in three ways. Now, for example, when a 3 volt battery is connected to a light, a current of 6 microampere is observed. What is the resistance of the light flamed here? So 3 volt battery, the electric source will be, potential difference will be 3 volt, and current will be 6 microampere. So the electric circuit can be shown here on the right side. So EMF will be what? 3 volt, and I equals to 6 microampere. And if the resistance R, we can define R equals to B by I. So we get the resistance equals to 500 ohm. 500 ohm. Now the SI unit of the electric resistance is the ohm. You have to remember this. So 1 ohm equals to 1 volt divided by 1 ampere. So per ampere, the potential difference is called 1 ohm. Now in laboratory circuit symbols, we can denote the rheostat connected with the resistance, which is called rheostat. The source of EMF will be and current flow from positive terminal to negative terminal here. So rheostat, due to the rheostat, the current flow of electron, that means current electricity will be less. So ammeter will be connected to measure the electric current, and voltmeter will be also to find out the amount of potential difference. Now, factors acting the resistance. The length L of a material, longer materials have greater resistance. You have to remember this. If the length is bigger, the resistance is also bigger, because length divided by 1 ohm, twice length the twice ohm. You have to remember this. The cross-section area A of the material, larger areas offers less resistance. So larger area will be less resistance. Suppose a cross-section area has twice ohms resistance, then if the area is twice, then resistance will be half. This is the properties of resistance. Now, in 3, the temperature T of the material, the higher temperature usually result in higher resistance. You have to remember, if the original length of a wire is resistance R naught, then if we give heat with a candle on the wire, then the resistance will be higher than the original resistance. Number 4, the kind of material, iron has more electric resistance than geometrically similar copper conductor. That means copper and iron. So resistance of iron will be greater than the resistance of copper. This is the temperature depending properties. Now, what is the resistivity or specific resistance? The resistivity rho is a property of a material that determines its electrical resistance R. It is denoted by rho. The recalling that R is directly proportional to the length L and inversely proportional to the cross-section area. That means by Ohm's law, mathematical expression will be capital R equals to rho L by A, or rho equals to RA by L. That means a specific resistance can be measured with this formula. Now, another example 3, the length L of a copper wire is required to produce 4 milliohm resistor. Assume the diameter of the wire is 1 millimeter and that the resistivity, that means specific resistor rho is of copper is this. So you must know the formula of cross-section area, pi d square by 4. So d is the diameter here given. So A equals to what will be 7.85 into 10 to the minus 7 meter square. Using the conventional transformation law of Ohms, R equals to rho L by A, we get the result this. Now, temperature coefficient. For the most material, the resistance R changes in proportion to the initial resistance R naught, and the change in temperature del T will be given by del R equals to alpha R naught del T. This is the change in resistance. This is the formula for finding coefficient of resistance. The temperature coefficient of resistance alpha is the change in resistance per unit resistance per unit degree changes of temperature. So we have to use this formula for finding the temperature coefficient of resistance, and it is also given by alpha equals to del R change in resistance divided by original resistance into temperature difference, which is unit is actually per degree centigrade. This is the example resistance of a copper wire is 4 milliohm at 20 degrees centigrade. What will be its resistance if the heat at 80 degree? Assume that alpha is given 0.004 per coulomb per degree centigrade. So R naught is given 4 milliohm and temperature difference will be 60 degree, 80 degree minus 20 degree. So using formula, we get the change in resistance will be 1.03 milliohm. So the total resistance will be R naught plus change in resistance. So R equals to given by actually 5.03 milliohm. Now, what is the electric power? The electric power is also power P is the rate at which the electric energy expanded or work per unit time. That means work done per unit time can be measured with electric power. So it is one kind of energy. So its unit will be also joule. The charge C, if the work done is QB, okay, work done will be QB, then power can be measured by work done per unit time. So QB divided by T, I equals to, since I equals to Q by T, so substituting Q equals to IT, we get P equals to BIT divided by T. TT cancel, then we get P equals to BI. So this electric power equals to potential difference multiply electric current. Now calculating power using Ohm's law, we can find the electric power from any two of the following parameters. That means current I, electric current I, voltage B, and resistance R. So example, a power tool is rated at 9 ampere. So we have to use Ohm's law, B equals to IR. That means from these three types. Now we can calculate this example. A power tool is rated at 9 ampere when used with a circuit that provides 120 volt. What the power is used in operating this tool? Actually, you have to calculate the electric power. Power equals to BI, just multiplying 120 multiplying 9, we get 1080 watt. The electric power unit will be watt. That means if work done per second is called watt. Another example, 500 watt heated draws a current of 10 ampere. What is the resistance? So you must know P equals to I square R, then R equals to P by I square. So we get R equals to result. Now summary formulas we have used in this slide. Electric current A equals to Q by T, 1 ampere per coulomb is called, per second is called ampere. So Ohm's law, three types of series. Now what is the specific resistance? R equals to rho by L by A and rho equals to RA by L. We have solved some real life example using these formulas. Now increasing the resistance decreases the flow of current. You have to remember we have used here voltage and resistance and electric current. So electric current will be less if resistance is bigger and the pressure, that means volt, is given higher, than electric current also higher. So this is a very funny example to understand what is the voltage, what is the resistance, and what is the electric current. Now the increasing this one, so increasing the resistance decrease the flow of current. That means after the flow of current, it will be happened. Okay, if volt is more, then electric current will be more, and if resistance more, then electric current will be less. A series circuit, so what is the drift velocity and current? Drift velocity is defined as the velocity with which the free electrons get drifted towards the positive terminal under the effect of applied electric field. So it is one kind of velocity of electrons which flow in the where from positive terminal to negative terminal. So drift velocity denoted by BD, which is equals to acceleration multiply time, relaxation time. So BD equals to AT, where BD equals to, and acceleration can be measured by E minus E into E bar by M. So I equals to any A BD. We can use here current is directly proportional to the drift velocity. Here BD is equal to drift velocity, I is the acceleration, T is the relaxation time, E is the electric field, and electronic charge, M is the mass of electron, N is the number of density of electrons, and L is the length of the conductor, and I is the cross sectional area of the wire. So we have to, this is the definition of drift velocity in a current, electric current. This is very important definition for you. Now what's the resistance? So now what is the current density? Current density at a point within a conductor is the current through a unit area of the conductor. Around that point, provided the area is perpendicular to the direction of flow of current at that point. That means current density can be measured by per unit area, electric current per unit area. That means we can denote is NEBD using the drift velocity. So in vector form, I equals to, this is a dot product of current density and cross section area, because cross section area depends on the diameter, or we can denote this diameter as a vector form. Now current density, this definition of the current density. Now resistance of a conductor is the opposition offered by the conductor to the flow of electron current through it. So resistance can be denoted by the potential difference per unit electric current. So resistance in terms of physical features of the conductor, we can denote I equals to any VD, any AD. That means VD equals to drift velocity. So we can use here rho R equals to rho L by A, where rho is the specific resistance. So it is equals to M divided by NE square T. So resistance is directly proportional to the length and inversely proportional to the cross-sectional area of the conductor, and depends on the nature of materials and temperature also. So resistivity depends upon nature of material and not on the geometrical dimension of the conductor. So R equals to, we can derive using the laws of drift velocity. So relation between drift velocity, specific resistance, length, electric field, electric density, and potential difference. So you have to use the formula here. When temperature increases, drift velocity decreases, and when a specific resistance increases, then length increases and potential and drift velocity decreases. So using these three formula, rho equals to this one, drift velocity equals to electric field divided by NE P, NE rho, and drift velocity equals to V divided by NE P, NE rho L. So conductance and conductivity. What is the electric conductance? So conductance is the reciprocal of resistance. Its SI unit is ohm meter. You have to remember it, ohm meter. And conductivity is the reciprocal of resistivity. Remember this. So conductivity of SI unit can be written ohm meter divided by per ohm meter. So temperature depends on resistance. Remember it. R equals to M divided by NE square T divided by L by into L by. When temperature increases, there will be no collisions of increases due to more internal energy, and relaxation time decreases. Therefore, resistance increases. So R equals to M divided by NE square T by L by A. That means temperature coefficient of resistance can be measured by alpha. You must know about this formula from previous slide. Alpha equals to resistance difference divided by original resistance multiply difference of temperature. So R naught here resistance at 0 degree, and RT is resistance at T degree, and R1 is the resistance at first temperature, and R2 is the resistance at second temperature. So if R2 is less than R, then alpha will be negative. You have to remember this. That means temperature coefficient will be less. Now, very important part, the color code of a carbon resistor. This is very important for you. The first two rings from the end gives the first two significant figures of the resistance in ohm. That means there are three rings, one gold, silver, and other is on other one. So the third ring indicates the decimal multiplier. You have to remember is there are 3 rings. So third ring will indicate the decimal multiplier. The last ring indicates the tolerance percent about the indicated value. So for example, we can use these 3 types of metal to measure the color code. This is actually BB Roy of Great Britain has very good wife. That means first B will be black. First B will be black. The second one brown. Then R will be Roy means red. U for orange. Y for yellow. And Z for green. And Britain blue. And has berry means violet. So good means gray. And wife means white. So using this sentence, we can memorize the whole part here. Okay. That means black, brown. And it will start with digit 0 to 9. There are 10 types of color. And using the sentence, BB Roy of Great Britain has very good wife. We have to memorize this color code. For color and tolerance will be, suppose gold color, this will be tolerance will be 5%, silver 10%, and if there is no color, then 20%. So in right side from the figure, actually for gold, first ring will be what? Brown, and then violet, then black. And so last ring indicates the gold. This is why 5% tolerance. Now for the silver, first one will be green, red, then blue. So last ring is silver because silver color. This is why it will be tolerance 10%. Now, if there are no color, this is why first ring indicates the brown, then violet, and then black. So there is no color. This is why 20% tolerance. So you have to remember this. This is very important for you. Color code for carbon resistors. So using this sentence, you have to memorize the whole 10 number of color. Now another color code for carbon resistance. So the color of the body gives the first significant figure. So body is actually blue dot. The color of the ends gives the second significant figure. The color of the dot gives the decimal multiplier. That means blue dot here. The color of the ring gives the tolerance. So color of the ring will be gold ring. So tolerance will be 5%. So we have to remember these 4 types of properties using this diagram. So there are 2 types of series combination of resistors, and other is parallel combination of resistance. And if the R1, R2, and R3, there are three types of resistance. So first resistance, the last part will be connected with the first part of the second resistance. The last part of the second resistance will be connect with the third part of first resistance, first point. So in this way, if we connect all the resistance, the connection will be series combination, and parallel will be what? The first part of the all resistance will be connected with one point, and the last part of the all resistance will be connected with another second point. Then we get the parallel combination. So equivalent resistance will be measured with this. Now source of EMF, the electromotive force is the maximum potential difference between the 2 electrodes of the cell when no current is drawn from the cell. If there is no current flow, then potential difference, electromotive force will be, or potential difference will be highest. So there are comparison between EMF and potential difference. EMF, electromotive force, is the maximum potential difference between the 2 electrodes of the cell when no current is drawn from the cell. That means the circuit is open, but the potential difference of the potentials between any 2 points in a closed circuit. So that means EMF will be the highest. It is dependent on the resistance of the circuit. It is proportional to the resistance between the given points. That means if the potential difference is high, then resistance also high. The term EMF is used only for the source of EMF. It is measured between the two endpoints of the circuits. Number 4, it is greater than the potential difference between any 2 points in a circuit. However, potential difference is greater than EMF when the cell is being charged. If we give extra charge to the source, then potential difference may be greater than electromotive force. So there are 4 comparison between EMF and potential difference. Now, internal resistance of a cell. How we can calculate the internal? The opposition offered by the electrolyte of the cell to the flow of electric current through it is called the internal resistance of the cell. Factors affecting internal resistance of a cell. Larger the separation between the electrodes of the cell, more the length of the electrolyte through which current has to flow, and consequently a higher value of the internal resistance. Number 2, greater the conductivity of the electrolytes, lesser the internal resistance of the cell. That means if the conductivity is more, then resistance will be less. The third one, the internal resistance of a cell is inversely proportional to the common area of the electrodes dipping in the electrolyte. So number 4, the internal resistance of a cell depends on the nature of the electrodes. So we can calculate EMF equals to potential difference plus potential difference, internal potential difference. Okay. So B equals to IR, you must know. I is the total electricity and R is the resistance of the whole circuit. And a small b equals to I into small r. Small r is the internal resistance of the internal circuit. So I b equals to can be calculated E divided by R plus R. The relation is called circuit equation. Remember this. Now, internal resistance of a cell in terms of EMF, electric field, EMF, and potential difference and resistance. So you must know equals to B plus B. So IR equals to E minus B. Dividing by B equals to IR, we get R by R. Here remember there is a mistake. R divided by R will be E divided by B minus 1. So determination of internal resistance by a cell, that means voltmeter method. We have to connect with a voltmeter. For open circuit, no current is drawn here, but closed circuit, their current is drawn. So current flowing from positive terminal to negative terminal, then potential difference is measured. Then if there is no electric current, then EMF will be measured, which is maximum value of EMF. So this equation can be used to measure the amount of internal resistance and in terms of EV. Now cells in series combination look like the resistance. Cells are connected in series when they are joined end to end so that the same quantity of electricity must flow through each cell. That means if we add 3 cells, small cell, C1, C2, C3, then this will be in a series way because electric current is same. So the EMF of battery is the sum of the individual EMF. You have to remember that all EMF will be sum. The current in each cell is the same and is identical with the current in the entire arrangement. That means the amount of flow of electric current is I. So the electric current of individual cells will be same. Number 3, total internal resistance of the battery is the sum of the individual electric internal resistance. So total EMF of the battery, what will be? NE. N is the number of identical cells. Total internal resistance of the battery will be internal resistance. Each internal resistance is R. So total will be NR. So total resistance of the circuit NR plus R. So current I equals to an EMF divided by E divided by total resistance. So if capital R is more and more less than an R, then capital R can be removed. That means I can be written as I equals to E by R. Now, if NR is more and more less than R, then I can be written as N divided by E by R. So as a conclusion, when internal resistance is negligible in comparison to the external resistance, capital R is the external and small r is the internal. Remember here, when the cells are connected in series to get maximum current. So these are the properties of cells in series combination. And you have to use the current I equals to N divided by NR plus R. So internal resistance R may be less, or external resistance capital R may be less. So if the less, then we can omit the resistance to get the highest electricity. Now cells in parallel combination. Cells are said to be connected in parallel when they are joined positive to positive and negative to negative such that current is divided between the cells. So there are three cells first part of each cell connected with one point, and second part of each cell connected to other point. There are potential difference same, but electric current not same. Whole electric current I can be divided into three parts. One is I1, I2, and I3. Okay, I1 for the first cell, I2 for the second cell, and I3 will be second cell. So now the EMF of the battery is the same as the of a single cell. The current in the external circuit is divided equally among the cells. Current will be divided into many parts. The reciprocal of the total internal resistance is the sum of the reciprocal of the individual internal resistance. So the equivalent resistance can be measured with this one. That means the total EMF of the battery is E, the total internal resistance will be what? R by N. Total resistance of the circuit will be R by N plus R. So current can be measured I equals to N divided by NR plus R. If external resistance R is more and more less than Rn, then we get I electricity higher. If the internal resistance is more and more less than external resistance, then we get I equals to E divided by R. So conclusion, when external resistance is negligible in comparison to the internal resistance, the cells are connected in parallel to get maximum current. Now current and electron drifts velocity. So consider a material where the current or electron is flowing. N is the free charge electrons per meter cube, and Q the charge per charge carrier, and A is the cross-sectional area of the material. The total charge Q, del Q in volume element moving past a point. That means del Q can be measured by any A del X Q. Here volume, change in volume equals to area in change in length. So if the charge moving with a average drift velocity BD, then the equation can be written as like this. And thus the electron can be written in terms of microscopic quantities. That means rate of change of amount of charge with respect to time equals to this. NQA BD. BD means what? Drift velocity. So now example for calculating drift velocity. 10 ampere flowing through a copper wire of a diameter 2 millimeter. So density of copper you must know 8.92 gram centimeter cube. That means 8920 kilogram meter cube. One free electron per copper atom. So atomic mass of copper what? 63.5 from periodic table. So mass can be calculated by using this one. Charge will be 6.02 into 10 to the power 23. This is the Avogadro number of copper atom. So to find the drift velocity BD, I equals to NEA BD. This is the formula for finding electric current using drift velocity. So electric charge will be 1.6 into 10 to the minus 19. Cross sectional area equals to 3.14 into 10 to the radius r equals to 2 millimeter. Diameter 2 millimeter, but radius will be 1 millimeter. So millimeter can be transformed to meter cube. That means 10 to the power minus 3. So we get cross sectional area 3.14 into 10 to the power minus 6 meter square. Still need n is the density of electrons in meter cube. So using copper properties, so n equals to what? A specific resistance rho, density of copper. So m mass, which can be calculated 8.5 into 10 to the power 28 meter cube. So solve for the electron drift speed velocity or drift velocity. Drift velocity equals to I divided by n EA. Just putting all the values here, we get the drift velocity. So drift velocity is 0.24 millimeter per second. That means 1 hour to move 1 meter. But electrons actually move 10 to the power 6 meter per second in material. Thus, we can say that 4 into 10 to the power 9 times larger than drift speed or drift velocity. Actually, drift velocity is more and more less than the original speed of electron. So how many times? 4 into 10 to the power 9 times. Very interesting. Now drift velocity or speed versus individual electron speed. So we can find individual electrons move at a very high speed, but in randomly direction. Current depends on the net velocity of a large number of electrons. Many examples of this in real life, as opposed to physics life actually. Passengers moving around on a cruise ship. Drift velocity equal to what will be ship velocity of ship. Air molecules bouncing around the inside the elevator. That means elevator velocity will be BD. People moving around on planet Earth. Velocity of Earth will be drift velocity. So this is the real life example for drift velocity or speed versus individual electron speed. Now electrons in the air. If the electrons move so slowly through the air, why does the light go on right away when we flip a switch? Household air have almost no resistance. The electron field inside the air travels much faster. Light switches do not involve. Which one will be? None of them. Actually, the electric field inside the air travels much faster. Electric field moves the fraction of the velocity of light, immediately moving electrons which fill the entire circuit. This is like a house full of water. When we turn on faucet, the pressure wave moves much more rapidly than the water itself. So electrons in the air. Electrons in the air, part 2. Oh, okay. So the electric field in air travels quickly, but didn't we just learn electric field equals to, that means EMF will be 0 inside a conductor. So true, it can't be the travel, and the electric field travels along outside the conductor, and E will be 0 inside the conductor applies. EMF source constantly replenishable electric field, but this takes energy provided by EMF source. So E equals to 0 inside the conductor. Now, Ohm's law is an empirical observation that the current in a material is proportional to the applied E field. Okay, so I is proportional to potential difference, current is applied voltage difference. Now, it's not a law in the sense of the other physical laws, only approximately true. This is the limitation of Ohm's law, violated completely by semiconductor and superconductors, but it is observed in a diverse range of materials over a very wide range of applied voltage difference. It can also be understood in terms of an atomic level description of current. So this is the actually limitation of Ohm's law. We have to remember this. Other than the physical law, it is not behave. So microscopic understanding of Ohm's law, consider a conductor with applied electric field E. Electrons within conductor moves at high speed 10 to the power 6 meter per second, but very small drift velocity. In our previous slide, we observed that. And undergo collision, mean collision time tau. So drift velocity and mean collision time related by acceleration will be actually velocity equals to acceleration equals to velocity divided by time. That means non-uniform velocity per unit time is called acceleration. So we get acceleration equals to E divided by ME tau. So using this formula, we can find the drift velocity, where L is the length of the material, and you use potential difference equals to L. So we can now write the current as I equals to NA EBD. That means BD is the drift velocity. Just using the same formula of the previous slide, we get a specific resistance equals to M divided by E square NE tau, which is called a specific resistance or resistivity, same words. So resistance is a product of two factors. One is resistivity, as property of the material. Length per area is geometrical dimension of material. So Ohm's law, collision time almost unaffected by electric field. Individual velocity are huge compared to drift velocity. We have compared it. Collision time is constant, so resistivity is almost independent of potential difference. But the resistivity is temperature dependent. You have to remember this. So specific resistance or resistivity is depend on temperature, but does not depend on potential difference. So there are table of resistivity, different conductors here, and specific resistance and temperature coefficient also given. So for conductors and semiconductors and insulators also, and alpha is the temperature coefficient of resistivity. So you can use in our experiment these values. So temperature dependence of resistivity, we have to use this formula, rho T equals to rho naught L plus alpha del T, where values are typically tabulated at 20 degrees centigrade. In our previous slide, all values are 20 degrees centigrade. So not true for semiconductor, which behave very difficult. So using this table, we can find one. So we can calculate at 80 degrees centigrade, resistivity will be 2.21 into 10 to the power minus 8. So resistivity increases by 32% as a substantial amount. This is an example for calculating resistivity coefficient and resistance, specific resistance. Now reading quiz for this part, when resistors are connected in series, the current in each resistor is different. The current in each resistor is the same. The voltage in each resistor is the same. So series, you must know the current in each resistor is the same. Then the second one is true maybe. So I hope you'll understand this. So this is the true one. Now series circuit. In our previous, we have series for cell, different cells, and combination for parallel and series. Now simple series situation, one battery, two resistors R1 and R2 are connected. Crucial common current. So loop starting at a from point A, which is red mark here. So at this point, we can we can give the 0 plus E means what? The movement of electric current from positive terminal to negative terminal. This is why E minus B1 and B2. So for, potential difference for the first point B1 and second one will be B2. So E minus IR1 and IR2. So we get the in series connection, the equivalent resistance RS will be R1 plus R2. So in series circuit, battery since equivalent resistance RS. So RS equals to, for a number of resistance, RS equals to R1 plus R2 plus R3 dot dot Rn. So for series circuits, we have to use this one, and you can derive also equivalent resistance RS equals to R1 plus R2 for only two resistance. For a number of resistance, we can write the last equation. Rs equals to R1 plus R2 plus R3 plus dot dot. So resistors in series, battery EMF will be 12 volt and three identical resistors. What is the potential difference across each resistors? Current is the same, so voltage across each center. So current same, why? Series this way. Now, if the light bulb are all the same in each of those two circuits, which circuit has the higher current? Circuit A, circuit B, both. Which one? Actually 12 volt, but in B, two resistance. This is why A will be actually same. Okay, so A will be the A has twice the current as B because single resistance in A. Now real EMF source internal resistance. So to calculate the internal resistance, small internal resistance will be small r. Real batteries have small internal resistance, lower effective potential divided to circuit I equals to E divided by small r plus r. So total resistance small r plus capital R. So effective potential difference will be E minus IR. So equals to this. So effective voltage will be this. Now loss of voltage is highly dependent on load. Just using these examples, we can find the different electric potential difference for different EMF and different internal resistance and external resistance. We can find different values of potential difference. So resistance in parallel, you must know in parallel, current split into several branches. So potential difference the same across the each branches. So potential difference equals to B1 equals to B2, but I can be I1 plus I2. So I equals to B by R. Just using this formula, we can 1 by RP. Where RP is the equivalent equivalent resistance of parallel connection. Works for any number of resistors. There are two numbers of resistance. One is R1 and R2. So we can denote it for n times resistor. Now resistors in parallel, more resistors are added in a parallel to circuit. How does total resistance between P and Q changes? So what will be actually decreases due to the equivalent resistance for parallel series. You must know equivalent resistance will be 1 by R1 plus 1 by R2 plus dot dot. This is why decreases. Now, if the voltage of the between P and Q, the circuit, how does total resistance between P and Q changes? Actually decreases. So just by using the circuit equivalent resistance, we get this. Now resistance, for example, this is a very important example for you. Find net resistance of the circuit connected to the battery. Each resistance head are equals to 3 kilo ohm. Note that the following figure, kilo ohm displayed as the kilowatt for some reason. So there are actually combination of resistance. Now combined first resistance and second resistance. So R1 2 equals to in series connection. This is why just sum of two resistance. 3 plus 3 equal to 6 kilo ohm. This converted to second, that means 6 kilo ohm. But 6 kilo ohm and 3 kilo ohm third resistance are in parallel connection. So for using the equivalent resistance for parallel connection, we get the parallel for the parallel R1 2 3 will be what 6 divided by 3, that means 2 kilo ohm. Okay, so this transform to single resistance of 2 kilo ohm in the right circuit. So observe that this equivalent resistance 2 kilo ohm with 4 resistance, number 4 resistance in series connection. So we can transform into equivalence resistance of what? R1, 2, 3 with 4 will be 2 plus 3. That means 5 kilo ohm. So 2 kilo ohm and 4 kilo ohm are in series connection. This is why just sum of two resistance. So this can be converted to into equivalence resistance of 5 kilo ohm in the right part. So 5 kilo ohm will be the now 5 kilo ohm, and the fifth resistance will be in parallel connection. This is why equivalent resistance will be R1, 2, 3, 4, 5 equals to 5 by 3. That means this transform to single resistance of 1.875 kilo ohm. So this equivalent resistance with sixth resistance will be in series connection. This is why the equivalent resistance will be R1, 2, 3, 4, 5, 6 equals to sum of these two. So 1.875 plus 3 equals to 4.875 kilo ohm. That means we get a single resistance after calculation of big resistance. So many resistances here, but they transform to single resistance with potential difference will be or EMF equals to 12. So if the light bulbs are all the same in each of these two circuits, which circuit has the higher current through the battery? Current A, current B, both the same. Really think yourself. The light will be actually B draws twice the current as A because there are two bulbs. In which current is each light bulb brighter? Which one is brighter, A or B? Circuit A, circuit B, both the same. Which one will be brighter? Current through each branches is unchangeable because B by R, because same current will be same. I equals to B by R. Household circuit or parallel paths. Actually, all devices are added in parallel, and each power outlets is 115 volt independent of others. Enough power must be supplied from connection to power company. Overload too many devices that requires a lot of current can draw more current than wires can handle. Overheating of wires, fire hazards. So this is from electric company. Now some circuit problem like the previous one. The light bulbs in the circuit are identical. What happens when the switch is closed? Both bulbs go out. The intensity of both bulbs increases. The intensity of both bulbs decreases. Nothing changes. Which one? So the switch closed, potential difference will be 12 volt. And because of the battery, B will be 12 because equals the resistance divide 24 volt in half. So after switch closed, nothing changes because voltage will be the maximum. The light bulbs in the circuit shown below are identical. When the switch is closed, what happens to the intensity of the so the intensity of light a bulb A increases, bulb A decreases, bulb B increases, bulb B decreases. So same will be happened. So which one is the actually A and B are identical? What happens when the switch is closed? B gets brighter and A dimmer. So because the calculation shows it. So thanks to everybody. I hope everybody is fine and you'll revise the whole class, and best wishes for you. Thanks to everybody. Bye for today.